Welcome to Higher Secondary Physics Online. The lectures cover the higher secondary syllabi in physics of most Indian boards. They are attuned to questions and answers and the solution of numerical problems. Any good textbook can be used as reference, including the NCERT textbooks, which are good, inexpensive, and freely downloadable from the NCERT website. Higher secondary maths is used when required. There is a link to a file called basicmath.pdf in the description box. This contains important maths concepts and results regularly used in physics. I encourage you to use it. At any time you want, you can pause the video and write down what you see on the screen. If you found this lecture useful, please press the like button. And now to the main lecture. Lesson 101. Units and dimensions. All physical properties have dimensions. All dimensions are measured in units. 7 selected properties themselves constitute the basic dimensions of the SI system of measurement, that is the de facto international standard. Legacy systems are the FPS, CGS and MKS, the last being a subset of the SI. Tabulated, these have dimensions on the left hand side, the properties being length, mass, time, current, temperature, mole and luminous intensity. Units and symbols thereof on the right hand side. For definition of the units, please consult your textbook or Wikipedia. Next subject, significant figures. Any real number can be normalized, that is, expressed in the form n equal to a into 10 to the power of b, where n is a real number having 1 is less than or equal to n, which is less than 10, and b is an integer, positive, negative or 0. A determines the significant figures. For example, 39.375 equal to 3.9375 into 10 to the power of 1. A has 5 digits, so the number has 5 sig fig. 0.0000278 equal to 2.78 into 10 to the power of minus 6. A has 3 digits, so the number has 3 sig fig. A result of n equal to 2.84 found after measurement means 2.835 is less than or equal to n, which is less than 2.845, correct to 3 sig fig. Whereas a result of n equal to 2.840, arithmetically the same, means 2.8395 is less than or equal to n, which is less than 2.8405, correct to 4 sig fig. From the standpoint of measurement, the results are different. We thus come to the important concept. A result that has or that is the function of 2 or more measurements has the same number of significant figures as the least number of significant figures among the measurements. For example, 5.78 gram of a substance occupies 1.2 cc in volume. Calculate its density in gram per cc, keeping the applicable significant figures in view. The answer: mass has 3 sig fig, volume has 2 sig fig, Therefore, the result has 2 sig fig. Density rho equal to mass by volume equal to 5.78 by 1.2 equal to 4.8 gram per cc, correct to 2 significant figures. Next subject, errors and small changes. Consider a polynomial function given by phi equal to kx to the power of a, y to the power of b, z to the power of c, where k, a, b, c are constants, and of course phi x, y, z are variables. Taking logs on both sides, ln phi equal to ln k plus a ln x plus b ln y plus c ln z. Differentiating d phi by phi equal to a dx by x plus b dy by y plus c dz by z. With delta x, delta y, delta z being the small changes in x, y, z, and delta phi being the consequential change in phi, we can rewrite this as delta phi by phi equal to a delta x by x plus b delta y by y plus c delta z by z. The maximum possible error or small change in phi is therefore delta phi by phi equal to the positive value of a delta x by x plus the positive value of b delta y by y plus the positive value of c delta z by z. Note the adjustment in sign. This is because x, y, z can change in either direction, and we are interested in the maximum possible change in phi. Note, delta phi by phi, delta x by x, delta y by y, delta z by z are all relative errors. Relative errors, which can be conveniently expressed as percentages. Question: we are measuring the density of a substance by measuring the radius of a perfectly spherical ball accurate up to 1% and its mass accurate up to 0.1%. What is the level of accuracy of the measurement? Answer: rho equal to 3m by 4 pi r cubed, which is equal to 3 by 4 pi into mr to the power of minus 3. Incorporating the observations made before this, we get delta rho by rho equal to delta m by m plus 3 delta r by r, which is equal to 0.001 plus 3 into 0.01, that is equal to 0.031. Therefore, the result will be accurate up to 3%. Our inputs are correct to one significant figure. So, we have to express our result correct to one significant figure only. Use of derivatives. Where the relation cannot be expressed as a polynomial, we deal in absolute and not relative errors. If y equal to fx, delta y is equal to dy dx multiplied by delta x, where delta x, delta y are small changes in the x and y variables. Question: resistances R1 equal to 100 plus minus 3 ohms and R2 equal to 200 plus minus 4 ohms are connected first in series and then in parallel. Find the equivalent resistance. Answer. For 1, R equal to R1 plus R2, or this is equal to 300 plus minus 7 ohms. This is a simple addition. For 2, the relation is 1 over R equal to 1 over R1 plus 1 over R2, which implies R equal to R1 R2 by R1 plus R2, which is equal to 100 into 200 divided by 100 plus 200, which is equal to 66.67 ohms. Differentiating this particular relation on both sides, we get minus dr by r square equal to minus dr1 by r1 square minus dr2 by r2 square, which implies delta r by r square equal to delta r1 by r1 square plus delta r2 by r2 square, or delta r by 66.67 square equal to 3 by 100 square plus 4 by 200 square, which is equal to 4 by 100 square. Delta r equal to 4 into 66.67 square by 100 square, which is equal to 4 into 4 by 9, which is equal to 1.78 ohms. This implies R equal to 66.7 plus minus 1.8 ohms, because the result is correct to 3 significant figures, which is 1 decimal place in this case. Where did I get 3 sig fig? A value of R1 equal to 101 or 102 or 103 ohms is a perfectly valid input, and this can only be expressed in 3 significant figures. Next topic, measuring instruments. The concept of least count. Figure 1 represents a common scale marked in centimeter and millimeter, and the scale has a least count of 1 millimeter, that is the minimum distinguishable distance between 2 unequal measurements. This implies the results have a plus minus 1 millimeter accuracy. We come to the concept that all measuring instruments have a least count. Next subject, micrometer or screw gauge. Figure 2 shows a micrometer or screw gauge. A equal to the screw pitch, which is the least count of the main scale, and B equal to the number of divisions on the circular scale or thimble. The rotation of B divisions moves the spindle forward by A. This implies that A by B equal to the least count of the micrometer. Vernier calipers. Refer figure 3. Observe carefully the main scale and its reading at A. Where the edge of the jaw resides on the main scale, and the vernier scale and its reading at B. The reading on the vernier scale where markings on the main and vernier scale coincide. The main scale division or MSD is in standard units, millimeter, centimeter, inch, so on. The vernier scale division or VSD is in artificial units, being set so that N1 VSD equal to N2 MSD, where N1, N2 are integer constants. Vernier constant VC of a vernier caliper is its least count. VC equal to 1 MSD minus 1 VSD. Question: calculate the vernier constant of a vernier caliper where 1 MSD equal to 0.05 centimeter and 49 MSD equal to 50 VSD. Answer: 1 MSD equal to 0.05 centimeter, 1 VSD equal to 49 by 50 MSD, which implies VC equal to 1 minus 49 by 50 multiplied by 0.05, that is 0.001 centimeter.